and myself, R.S. Chatterjee from Geosciences Department. Okay. So geological hazard. So you know by now that what is a hazard and how to define a hazard, and what is risk, what is vulnerability. Okay, there are different terms are used in hazard studies, and now in this particular class we'll be discussing on the geological hazards. You know that naturally occurring hazards that can also be induced or maybe generated by some anthropogenic causes as well. Okay, but the hazards are of geological origin, so then only we can call them geological hazards. So once again I am defining. So geological hazards are such hazards, those are naturally occurring, okay, and or they can also be produced by anthropogenic reasons, but all such hazards are of geological origin. Okay, so then only we can call them geological hazards. So we know that potentially damaging natural hazards are generally three types, isn't it? And one of them, most important group rather, is geological hazards group. Okay, so geological hazards, meteorological hazards, and climatic hazards. Broadly, we classify into three groups of natural hazards. Now, in geological hazards, this can be produced due to some internal and external geological processes. Okay, some are produced by the external geological processes, and some are produced by the internal geological processes, and some are due to the interaction of these internal and external geological processes together. Okay, so these geological hazards, those are produced due to these external geological processes. Okay, they are generally called this exogenous. Okay, so exogenous means here the forces responsible for these hazards, this forces origin is external. So the force is available external. This force is available on the Earth's surface external. Okay, so that is why we define them exogenous. For example, mass movement, and under this mass movement, you can mention like landslides, then avalanches, then rockfall. Okay, so these are the different kind of mass movement, and there are many more like debris flow, okay, soil flow, like this, and then riverbed erosion, road cutting. So these are these geological hazards where the forces responsible for these hazards are available outside, external, and essentially this is due to the force of gravity. Okay? So due to the force of gravity, these hazards are happening. And endogenous, here the force which is responsible for these hazards, so this force, the source of this force is internal, from the inside of the earth. Okay, then what are these hazards? Like earthquake. So earthquake took place due to the rupturing of the earth crust, and the force comes from inside the earth. Similarly, volcanic eruption and tsunami. The tsunami, it is there in the externally, it is happening on the sea water, but the force which causes this tsunami, no, this force is coming from internal, this interior of the earth, okay, due to the faulting of the earth crust. See it? So this force which is coming from inside the earth, then it causes this sea water to inflate, and these tsunamis are happening, isn't it? So, but that is why we can name them like earthquake, volcanic eruption, and also tsunami, where basically there is interaction of the external and rather internal and the external, this geological processes is involved. Okay. Now there are some geological hazards; those are essentially of anthropogenic origins. These are not naturally happening, but due to the anthropogenically induced hazards. What are they? Like mining hazards. In case of mining, like if you say in case of coal mining, that there is a major problem of coal fire in many of the coal mines, particularly in case of China, in case of India. Okay, and there are many other coal fields in other areas like even in USA. Okay, so this coal fire is a big problem, and it is worst problem in China and India. coal fire is a big problem. Then there is land subsidence or roof collapse due to the subsurface or underground mining, and sometimes also due to the subsurface coal fire also. So this land subsidence and roof collapse, that causes lot of hazards and lot of damages and also loss of life. And urban hazards also, sometimes we see there are urban hazards of significance due to groundwater depletion, and this groundwater depletion is anthropogenically induced because of the high rate of groundwater pumping. Because of the high rate of groundwater pumping, the aquifer gets depleted, and then aquifer compaction takes place, and the land gets subsided. And sometimes the subsidence is so high that this differential subsidence causes the cracks on the building, on the houses, and sometimes even collapse of many of the houses. Okay, although this kind of damages or this kind of hazards are not of very high intensity in nature, but it happens slowly. So this is one of the urban hazards, and that happened due to the underground, this groundwater depletion due to the high rate of groundwater overdraft or groundwater pumping. Okay. Now coming to the individual hazard, first it is the landslide. We will discuss on the landslide. So this is the geological hazard and naturally occurring, and sometimes it is also anthropogenically induced by the road cutting. Okay. So landslide, although it is happening naturally in most of the cases, but it also happens due to this anthropogenic reason also. I'll discuss on that. So what is a landslide? Landslide is basically a kind of slow failure, and it is a mass wasting process, isn't it? And it is a serious geological hazard, and it can result in major loss of life as well as loss of property. So as I was discussing, that it is a mass wasting process, and it represents the movement of a mass of rock, sometimes debris, okay, rock fragments, or the earth, that means the soil, down the slope under the influence of the gravity. Now on the right side, you can see the illustration, this illustration of different schematic diagrams rather of different kind of landslides. So different types of landslides. It was initially given by this Rudin and Barnes in 1996, this classification of the landslides. And later on, it was modified by them in 2009. And you can see that the geometry of the slip surface or geometry of this landslide surface, you can see, like here, it is like a curved surface, rotational landslide. Here it is a planar one, translational landslide. Here you see these block slides, isn't it? Block of rocks it is going down. And here you see there are the fragments of rocks, big chunks of rocks are falling down. This is a rock fall. And here you see this is the tuffles. Okay, these blocks of rocks are jumping and falling down. In this case, you see there is a debris. Debris is flowing down. But here it is not simple flow, but it is the very high rate of flow. High rate of this you're moving down. That is the debris avalanche. So debris flow and debris avalanche, there is a difference. Now you see this is the earth flow. Okay, that is the very finer materials are flowing down. On the other hand, you see in case of creep, here the movement is very, very slow. Very slow movement, but this slow movement is very, very useful to identify that there may be in the future, there may be this big landslide can happen, isn't it? So this creep is very slow movement of the landmass. And here it's a lateral spread. So the different types of landslides are discussed schematically in this illustration. And here you see this table is very interesting one. Depending on the type of the movements, what are the different types of movements like falls, topples, slide, spread, and flow. Isn't it? So these are the different types of movements. But depending on the types of movements and depending on the type of the materials involved in this mass movement, like bedrock or debris, predominantly coarse rock fragments or debris, or predominantly finer materials or soil or earth materials, these landslides are classified into different types. Like here, for example, depending on the material and the type of the movement, it is a rock. And if it is slide, then the same material is bedrock, but the movement is slide, then it is a rock slide. Again, if you go to here it is the movement is false, but the material is debris, then it is debris. false. And if it is flow, the movement is flow, but the material is debris, then it is a debris flow. Similarly, for the earth materials, it may be earth flow falls, it may be earth slide, it may be earth flow. So different kinds of landslides you can categorize depending on the type of the movement and depending on the type of the materials. Now, based on this activity at this moment, whether this mass movement process or mass wasting process is ongoing at this moment, whether it is active at this moment or it is non-active, these landslides can be grouped into two. One is active, another is non-active. Okay, there are two broad groups of landslides, and under this non-active, again, it can be further classified into two. That is, one is dormant. So anytime landslide can happen. It is now slipping, isn't it? It is a slipping landslide. At this moment, there is no movement, but anytime it can happen. So this is dormant landslide. Another one is there was old landslide. The material has been moved down, and there are a lot of accumulation of materials has happened, and the slope has been finally graded, and the slope has been stabilized, and there is no question of landslide in the future. Okay, so it is non-active and it is stabilized, and it is a safe place now at this moment because it is a stabilized one. Okay, so this is the two groups under this non-active class. Now, based on the geometry of the slip surface, although I have discussed in the illustration before, so broadly there are two groups. That is, one is translational, where the slip surface is planar. Another is rotational, where the slip surface is circular. I'll show you one classification with a schematic diagram to understand more about that. Based on the slip surface, how we can classify landslides. Now we see these field photographs, spectacular field photographs taken by Dr. Sarkar. You can see here there is a planar failure here, okay, where the slip surface is planar. Okay, this is a translational landslide, and here it is. You see here it is a debris. It is a debris flow or debris slide, and in this case you see the big chunk of rock is vulnerable. Anytime it can fall down. And you can see there are many rock fragments are falling down. So it is an example of rock falls, isn't it? So predominantly rocks are falling down, but there are your debris, there are the earth materials are also falling down. Okay. Now, what are the criteria for identifying landslide? What are the characteristics for identifying landslide on the remote sensing images? So that we discuss in this slide. So identification of active landslides. So if you want to identify active landslide on satellite image, we look for scar on the earth surface, and this scar will be very, very clear on the satellite images, isn't it? And when there is scar, then you will not find any vegetation there. So if there was initially vegetation cover, you will not be able to see any vegetation cover now after the landslide happens, isn't it? So if you can see the scar on the earth surface on satellite image, or there is no vegetation, then you can identify landslide. I'll show you in the satellite image. So how you can identify active landslide? Based on visual interpretation you can do, simply by visually analyzing, visually looking at the image, or automated technique, okay, like image segmentation technique you can adopt, and you can identify, even at the pixel level, you can identify the landslide areas, or using another your automated technique like multitemporal change detection. Multitemporal change detection technique also you can adopt, and you can identify, you can detect, and you can map the landslide areas. Isn't it? This is for active landslide. Now, if it is for old and dormant landslide, then we have to look for this break-in slope, where there is a break-in slope, where the slope, there is some changes in the slope, and suddenly the slope becomes gentler, and there are a lot of materials has been accumulated, particularly thick soil we find at a particular place where the slope is less. That means here the old landslide materials are accumulated, and based on that we can identify. And if there are this thick soil is available and the slope is gentler, then what will happen? The vegetation will grow. So depending on the differences in the vegetation pattern and vegetation density, because if there are accumulation of material, particularly soil kind of materials is there, and slope is gentler, then vegetation density will be more. So depending on the nature of the vegetation cover itself and vegetation density, we can identify that perhaps there is old landslide zone is occurring in this particular area. So this is the characteristics of identifying old landslide. Now, if you want to identify the zone potentially hazard for landslide, that means if you want to identify the zone where landslide can happen in the future, so potential landslide zone, then what do we have to look for? We have to see where the slope is more. If the slope is gentler, then there is a chance of landslide is less, isn't it? Why? Because landslide is basically a slope failure. Mass wasting due to slope failure, isn't it? So steeper the slope, it is more vulnerable for landslide. Then if there is landmass is undercut by stream or waves at some place, so then the foundation becomes weak. Foundation support is not there. So this is another potential zone of landslide. Then where the drainage concentration is very high or seepage concentration is very high, then what does that mean? Pore pressure will be more. Pore water pressure will be more. So then what will happen? It will exert pressure. It will exert force on this rock mass and it will move down. Isn't it? And what else? The concentration of weak structural planes. Where there are the weak structural planes, means fractures or joints are more, and they are opening, their density, their intersections, their aperture, opening and aperture is the same. Okay, so depending on that, we can assess that this is a particular zone which is very vulnerable for landslide. Why? Because along these fractures, water will percolate. Okay, and it will cause this rock mass to move down, to flow down. Okay, and areas surrounding recent landslide, areas of old landslide. So these are the areas where landslide can happen. Now you see this example in Uttarkashi landslide that happened long back in 2001. In the IIRS list 3 image, you can see very clearly, you can identify the scar. I'll show once again in a high resolution panchromatic image also, and you can see how the landslide scars can be very clearly visible and you can map that very easily. Okay, and if the image is high resolution, like your Cartosat panchromatic image, okay, then this landslide scar will be more clearly visible. And this, by identifying these scars, the landslide inventory can be mapped. This is one of the examples in and around Okimot. These landslide scars are identified and mapped, and this is the landslide inventory of the Okimot area in 2013. Now we see, depending on the geometry of the slip surface or the landslide surface, as I told you earlier that we will discuss with some your schematic diagrams. So now you see that there are different types of landslide depending on the geometry of the slip surface. Like here you see this is circular failure or rotational landslide. Okay, like inverted the spoon, that is the slip surface. The planar failure, that is the translational landslide. Then the wedge failure, where wedge failure happens, where there are two structurally weak planes, two joint planes are intersecting. Okay, two joint planes are intersecting. Then this block of rock mass becomes vulnerable and it can fall down like a wedge of rock mass, isn't it? Then the toppling failure, when the dip of the beds or the weak planes is opposite to the slope, then this kind of failure takes place. Now you see on the satellite image and on the ground-based this photograph, how this landslide can be compared. See on the satellite image, very clearly you can see the landslide scar, and on the ground, if you take a photograph in a small scale, you can see how it looks. And if you make a large scale, by extending view or by zooming this area, then you can see this is the scar. Okay, and this landslide very clearly we can identify from this ground photograph that it is a planar failure. That means it is a translational rock slide. On the other hand, you can see here it looks like a spoon, isn't it? And the surface is curved, circular surface. So this is a circular, this your slip surface, and the rock mass is rotating. Okay, it is first going down, then going horizontally, then again going down the slope. So this kind of movement is the rotational kind of movements. You can see here that this slide is rotational landslide. You can see on the satellite image, it is very clearly you can identify it, and on the ground. Now, what are the different causative factors of landslide? Because if we can understand well the causative factors, then we can do the hazard zonation. We can say that this is the area where the likelihood of landslide occurrence is more, or the zonation of the landslide potential hazard zonation we can do, depending on this occurrence of the causative factors in that particular area. And what are those causative factors? Broadly, it is grouped under geomorphology, so geomorphological factor, then topography, then topographic factor like slope amount, slope direction, slope shape. Okay. Then geology. Under this, there is the lithology or rock types, geological structures of weak plains, and geotechnical properties of the rock mass or engineering geological properties of the rock mass. So this is the geological, this your factor. And then land use, land cover. What is the land use, land cover type of that area? Okay. And hydrology, like what is the rainfall intensity, rainfall duration. Okay. Particularly this groundwater condition and the pore pressure. So rainfall intensity and duration, it also comes under the triggering factors. But what is more important under hydrology is the groundwater condition or hydrogeological condition of that area. What is the porosity, permeability of the rock mass? So those things are more important. Okay. Now coming to the triggering factors. So we can say that what is the likelihood timing of the landslide? When landslide can happen? Okay, that kind of modeling you can do. And the previous slide, what we have discussed, the causative factors. So depending on the causative factors, you can make a geological hazard zonation, potential landslide hazard zonation. You can say, so this area, okay, it is more prone to landslide. But when these triggering factors will exist there. If there is no triggering factor, although it is high hazard zone, landslide may not happen in this area. And what are those triggering factors? Like if in the high hazard zone, there is high rainfall. Rainfall intensity is very high and rainfall duration is very long. In this high hazard zone, so then what will happen? Landslide can take place immediately, okay, in a few days itself. Or if there is an earthquake, moderate to high magnitude earthquake, so a lot of shaking takes place and this zone is a high hazard zone, then what will happen? That some of the rock, these fragments, some of the blocks of the rock masses can fall down. Rock slide can take place, isn't it? So because of the earthquakes, this as a triggering factor, landslide can take place. Then anthropogenic factor, and in a high hazard zone, if there is the roads, if you cut the roads for broadening, if you do the mining, if you do some developmental projects in and around that high hazard zone, then what will happen? Landslide will take place. Okay, so these are the anthropogenic factor. And then riverbank erosion. If a particular river causes lot of riverbank erosion, then the slope on either side of the river, this will be very prone to landslide. Now, depending on these causative factors, we can make this potential hazard zonation of landslides. And what are those different methods? How we can do this potential hazard zonation? One is a direct method. Direct method, in this method, what we do? We do the geomorphological mapping, landslide inventory mapping, landslide distribution analysis, their statistical analysis of the landslide, their frequency. Okay, and based on that, we can identify that this is the area where landslide occurrence is more, landslide likelihood is more, landslide frequency is more, so landslide hazard will be more. It's a direct method. An indirect method is there are grouped into two types. Two groups. One is data-driven, that is essentially statistical method. Okay, that's one method like information value. Another is knowledge-driven. This is by the method of index overlay data integration or fuzzy logic data integration. We can do this knowledge-driven indirect method can be adopted for landslide hazard zonation. This is an example method for landslide hazard zonation. Okay, here you see how we proceed. First, we need to have this satellite image. And satellite image should be georeferenced, and depending on the scale of the hazard zonation map you need, you have to have this your image resolution, medium resolution to high resolution. Okay, if you are interested in 1:10,000 scale, 1:25,000 scale hazard zonation map, then we should go for the high resolution satellite image. And if you are going to prepare 1:50,000, even medium resolution image can be. Okay. So satellite image, spatial resolution, their multispectral image, as well as micrometric image, we should procure, and we need to georeference, or we have to procure georeference satellite image. Okay. Then we have to identify the area, like what is the route corridor, what is the area of interest, that we have to demarcate, and after that we have to interpret along with other ancillary data like digital terrain map, like Survey of India topographic map or other topographic map depending on the country where you are doing this kind of hazard donation map, and other thematic maps. Those are existing, those are available with you, previously prepared, and the literature. With that, all those things, taking help from all those things and essentially from the satellite image, we prepare these themes, prepare these maps, prepare these layers like rock types layers, geomorphology, lineament and geological structure, land use, land cover, slope map, slope amount, slope aspect, that will be slope direction and slope shape, drainage map, rock weathering. So these kind of all kinds of maps we prepare. Then we go for field investigation, verification, ground truthing for validation of these maps. Then what we do? We need to integrate them in a GIS platform, and then finally we generate the landslide hazard zonation map based on a particular integration algorithm used. As I discussed in the previous slide, different kind of data integration algorithms. And then the risk assessment we can do, and mitigation plan also we can prepare. This is an example. You can see this is the landslide hazard assessment in Uttarkashi area. So here there is one hazard map was prepared in 1:50,000 scale. Okay, so using all these positive factors, and this is this hazard map 1:50,000 scale was prepared in the late 90s, that means 1999, 2000, something like this. This map was prepared, and here you see in and around the Uttarkashi, this zone was identified as the high hazard zone. And then what we see in 2001, there was landslide occurred. This is the before this landslide. This is satellite image, and after this landslide, you can see this is the Varunavat landslide, trident-like landslide, inverted trident-like landslide. You can see that occurred in 2001. Isn't it? So this landslide you can see on the panchromatic image also. You see here there's nothing, and here you see these landslides here. Okay. So now again we have relooked and we have prepared the landslide hazard donation map at higher spatial resolution, because initially it was prepared in 1:50,000 scale. Now we are preparing in 1:10,000 to 1:25,000 scale, because our scale of this hazard donation map is very high, that is 1:10 to 1:25,000. Then you need this your input data layers. Okay, that also need to be very high resolution. And for that purpose, what we used? Airborne high spatial resolution images as well as high resolution satellite images we have used, and using those high resolution images we prepared this landslide incidence map, structural map, geomorphological map, and land use land cover map. Then we prepare this your landslide hazard donation map once again, okay, and landslide risk map depending on this at higher resolution at a large scale. This landslide hazard donation map and the risk map was prepared. And here it is the landslide management plan that was prepared earlier at 1:50,000 scale. You can see the panchromatic view of this Varunavat landslide. Okay, this is the ground view of this Varunavat landslide. You can clearly see how the landslide occurred. And there is another method is there, that is the deterministic method, that is based on the factor of safety. Okay, to see whether a particular slope is stable or not stable, that we can assess or we can determine. That is why this method is known as a deterministic method. And what is the basis of this method? It is the factor of safety, whether the topographic slope is safe or stable or not. How to do that? By the ratio of the sum of the resisting forces, the forces which resist slope failure, and the forces which drive slope failure. We take the ratio, okay, and if the ratio is greater than 1, we can say that that particular topographic slope is stable and safe. But when it is less than 1, then that particular topographic slope is unsafe and unstable. Here is the mathematics, how we do that. I am not going to the details at this moment. Now we are going to the next kind of your geological hazards. So before that, few more slides on landslides. Like landslide movement detection is very, very important. Landslide movement detection and monitoring by spaceborne geodetic techniques. Why it is important? Because if we can map the slow movements of the landslide, okay, slow creeping movements of the landslide, then the slow movements of the landslide help us to model that when this landslide is going to take place in the near future. So here this is an example of a landslide movement study by the spaceborne geodetic techniques, that is differential interchromatic survey is one of the very important spaceborne geodetic techniques used for land surface deformation, monitoring, land surface deformation measurements. This is a spatially continuous method. That means you have measurements in all the points, in all the pixels, and this measurements precision is millimeter to centimeter. Okay, so this is, you see, this is your area, that is in France. Okay, this is the example I have taken from Kuno et al. And you see the difference in interprograms at different time intervals, like 3 days, 6 days, 9 days, 9 days, 12 days, and 15 days. In some cases, you see this interprogram, the color cycles, which is known as fringe. Okay, which is known as the fringe or differential phase cycle. Okay, it's very clear. In some cases, this is not clear. There are more noise. And each phase cycle, you know, it needs lambda by 2 land surface movement. And lambda, you know, what is the value of lambda? Lambda is only few centimeters, depending on the radar wavelength used, depending on the radar pulse used. If you use C-band, for example, here the wavelength is 5.6 centimeter, and each phase cycle, that means each fringe or one color cycle is equal to lambda by 2. That means 2.8 centimeter. Okay. So now, counting this number of these phase cycles, you can yourself manually, you can say that where the movement is more and where the movement is less. Like here, if you take this example here, you see here the number of phase cycles are more, and here the number of phase cycles are very less. So the maximum movement direction, maximum landslide movement is happening in this direction. This is the maximum slope or maximum movements of the landslide. Similarly, here also you see. Okay. So landslide movement vectors you can also map by this technique. See, we also did this similar kind of these studies in Garhwal, Himalaya. Okay, using IIRS, LDSAT, ALOS, L-band, ALOS pulsar data, and recently we are doing with the Sentinel-1 C-band SAR data. Here you see this is this Alaknanda River Valley that landslide movements have been identified by this technique. Okay. Similarly, reservoir-induced landslide, like Terry Reservoir. In and around this Terry Reservoir, all the slopes there are, because of this your pore water pressure, this landslide movement is taking place. And these landslide movements can be mapped by this technique nicely. Similarly, in the natural reservoir like the Nainidal Lake, okay, in Kumaon area, you can see there are some your road, your cracks or something, your damages are reported previously, and there are the mass wasting or your slow movements are happening definitely. Otherwise, why this kind of these mass movements are happening, isn't it? So that we have made some attempt on studying this, what kind of movements are taking place in different parts. And you see here, there are some of the slopes, particularly in this particular area, their movement is much. And this is the technique we have adopted here. It is an advanced differential interchromatic technique and known as differential technique known as permanent scatterer interchromatic SAR technique. So here the individual information is coming from individual pixel. So this is pixel level information about the land surface movement due to the slope failure or due to the landslide that we can map here. Here the movement is more. Again, here also movement is more. Okay, and here movement is little less. That is the legend here you can see. So here the movement is more subsidence. Okay, and here the movement is uplift. Uplift subsidence, it is the convention with respect to the position of the radar satellite, and what is the slope of the terrain is important. Depending on that, sometimes it will appear like it is uplift or it is subsidence. Actually, it is on the opposite slope of the terrain. Now coming to another geological hazard, that is earthquake. Okay, an earthquake, you know, this earthquake is caused by a sudden rupture of the earth crust, isn't it? Here, elastic rebound theory is one explanation of how earthquake occurs. Okay, elastic rebound theory, that is in the next slide. That is the elastic rebound theory. Now, if you see Here in elastic rebound theory, how we explain this? The stress builds up in rocks of the earth crust and strain is accumulated. And as the stress is released, it bounces back without any permanent deformation as long as it is strained elastically. So normal rocks can accommodate only a small fraction of this total this strain as elastic strain, 1 to 2%. And beyond this limit, there is permanent damage or permanent deformation takes place. And finally, a rupture of the rock mass takes place. Okay, so this is, I'll come back to this slide. You see, that is how it happens. So this is a fence you can see here, and if it is deformed, and this is the weak plane develops, okay, then this is the movement. Due to this movement is like this, depending on that, this rock mass is deformed. But because it is deformed initially elastically, so up to that elastic limit, it will deform, and then their rupture will take place. And after this rupture, this two blocks, it will be divided into two blocks. So it will make two blocks, and one block will move in, two blocks will move in two different directions, isn't it? Due to this rupturing of the rock mass. And then what will happen? It will bounce back to the original undeformed shape. And because of this rupturing and because of this earthquake, the energy will be released in different kind of waves like P waves, S waves, and surface waves. Okay, primary, secondary, and surface waves. Now you see, this is the statistics of the earthquakes globally happening. That we see that there are thousands of small earthquakes. Small earthquakes means magnitude 3, 4, something like this. Okay, even up to 5 magnitude earthquakes. These earthquakes are happening thousands every day. So every day, the thousands of small earthquakes are happening all over the globe. But medium to large earthquakes, that is the magnitude is 6 to 8, that occurs all over the globe on an average once every month. So one of this kind of earthquake on an average is happening in some part of the earth. And strong earthquake, that is magnitude greater than 8, it is occurring on an average one earthquake in a year. So that is the frequency of earthquake you understand. So you cannot prevent earthquake to occur. Earthquake will take place. So then the mitigation measures, preparedness is important. Understanding about the earthquakes, where the earthquake is going to take place, what kind of damage will take place. So this kind of knowledge is very, very important for earthquake hazard studies. See, here for understanding the earthquake science, we need to know plate tectonics versus earthquakes. Where earthquakes occur? Earthquakes essentially occurs along the boundary of the plates. The geographic locations of earthquakes coincide with the plate boundaries. You see, these are the earthquakes all along the plate boundaries. Here different alphabets are given. I will explain that. This is S, M, and D. What is S? Shallow focus earthquakes. Okay, depth is shallow. M is intermediate focus. Okay, intermediate depth. And D is deep earthquake. Okay, so here these earthquakes occur along the plate boundaries essentially, but it can also occur in intraplate earthquake is also possible. And there are 7 major lithospheric plates and many minor plates are there. Now you see there are types of plate boundaries are different. The plate boundaries can be convergent, it may be transform faults, it may be divergent. Convergent means subduction zone, where one lithospheric plate is going down the other plate. Okay, so and while it is colliding and going down the other plate, so it is, this plate is getting destroyed. Okay, so the part of this lithospheric plate, not the entire plate is not getting destroyed. So here where there is your collision takes place, so there are some destruction is taking place. This is the subduction zone, isn't it? And this convergent plate boundary or subduction zone is the source of the large earthquakes. And many of the earthquakes are deeper in general in this particular plate boundary. Now with divergent plate boundary, this is these spreading ridges like mid-oceanic ridge. Okay, here the source of the small earthquakes and they are shallow earthquake. Whereas transform fault, this is another kind of plate boundary. Okay, this is the source of the medium to large earthquake. I am not going to much details into that. So many of you are very much conversant on these plate tectonics and plate boundaries. Now, there's one important, your spaceborne geodetic techniques, that is the interchromatic SAR that we have already discussed in case of landslide. That differential interchromatic SAR is very, very important for mapping and monitoring this post-seismic and interseismic land surface displacement due to crustal deformation and due to earthquake. And this is the example of the first example of the earthquake study by this differential interpolated SAR technique. You know, this Landers earthquake, which occurred in 28 June of 1992, this is the earthquake was for the first time, it was shown by this your satellite-based or spaceborne interpolated SAR technique. And this is the first example of interpolated SAR technique which shows the land surface deformation due to earthquake. For the first time, interpolated SAR was used to show land surface deformation for any kind of geological hazard, for any kind of movements. And this is essentially for the earthquake. And this Masonnet et al., they published, this is the first paper on differential interpolated SAR for land surface deformation, and it was published in Nature. Okay. And you can see here, this is the white lines, these are basically the rupture lines, fault lines. And each of the color cycles, they are basically the differential phase cycle or this differential interpolated SAR or D-insert range. And each range is lambda by 2 displacement. And lambda, you know, and lambda, you know, is the radar wavelength. Okay. Now going to this another example, that is the BAM earthquake. In case of BAM earthquake, that is happened in 2003, and it is magnitude is 6.5. Was Landers earthquake was 7.3 magnitude. BAM earthquake was much less, only 6.5 magnitude. Okay, although this your property loss was immense in case of Landers earthquake, but there are the loss of life was quite less, very less. But here in this case, BAM earthquake, although the magnitude only 6.5, the loss of life, you see, 43,000 people died in this earthquake. Okay, and this rupture is a 20-kilometer long rupture. And what is the main reason of this? More damage, more loss of life? Because it was a very shallow earthquake, only 4 to 5 kilometer deep. That is why it was very intense. Okay, and you see, this is the area where this earthquake occurred, was the epicenter of the earthquake. Before the earthquake, you see, this is the ground photograph, and you see after the earthquake, completely damaged. This is the radar image, this is the your amplitude image or the intensity image, and this is the coherence image. Okay, and this is an interprogram, raw interprogram. This is a filtered or topographic compensated interprogram. And this is finally the displacement map after phase unwrapping. And this is the displacement vectors due to this earthquake, and this is the rupture and the displacement, how it take place. You see, it's like a strike slip movements, isn't it? This is moving up and this is moving down. Now, in case of Nepal earthquake, which occurred recently, okay, in 2015, there is 7.8 magnitude earthquake occurred, 80 kilometers northwest of Kathmandu city. That is on 25th April 2015. And again, there is a 7.3 magnitude earthquake occurred. That is a major aftershock. That's 70 kilometers northeast of Kathmandu. That means 140 kilometers east southeast from the main shock. And that occurred, that happened on 12th May 2015. It's not very far from this main shock. And in between, there are many aftershocks of 6 and above magnitude aftershocks happened. And if you see the total number of aftershocks in few months, hundreds, thousands of earthquakes occurred, thousands of aftershocks. And this, see the pattern of distribution of the aftershocks. All the aftershocks are aligned in a particular pattern. East, southeast direction. All the aftershocks are aligned. You see, this is the geological features, NCT, main central thrust. This is the main shock, and this is the major aftershock. Okay, and this is your satellite image showing this area. Now you see the displacement map by the differential interpolated SAR technique. This is by L-band, allows to L-band SAR. You see, this is the distinctly you can map this uplift region and the subsidence region, isn't it? While we use the C-band radar set 2, we can map also very nicely and more precisely, okay, because the wavelength is shorter, so the precision of measure is better, okay. So you can see this is the displacement in case of C-band, and what happened, how much displacement, what is the nature of displacement. You see here, uplift is around 165 centimeter and maximum subsidence around 60 centimeter. This is what we can study from here. Now, if you see the MMI intensity, that is the modified Mercalli intensity, Okay, this scale of this 1 to 12, you can see here it is this damage due to the main shock, and due to the main shock and aftershock together, this damage we can find in the strong, very strong and severe class. That means these are 6, 7 and 8 MMI, this intensity class we can find in this due to this Nepal earthquake. Just one example you see in the Kathmandu area, this is the high resolution satellite image. There are a tower, you see this is completely collapsed. This is reduced to rubble. That is what you can see in the digital globe World View 3 image. Before the earthquake, that is in October 2014, and after the earthquake, that is 27th April 2015. You see, these are the rubbles. No, nothing. This tower is completely destroyed. Many damages, many landslide occurred due to this earthquake. Lot of damages, lot of loss of life and loss of property. Now, if you see, look back, the Chamoli earthquake that occurred in 1999. Okay, magnitude was not very high. Okay, 6.6 magnitude, and here also there are a lot of damage took place. More than 2,000 houses damaged and 100 persons killed. This is you see the isoseismal MMI map. Here you see this is the red zone, means it is the 8, means extreme, severe damage, severe intensity. Whereas this purple one, this is the very strong intensity. The other area is strong. Okay? And see, before the earthquake and after the earthquake, you can find many landslides. Due to this earthquake, due to this ground shaking, many earthquake occurred because of this. Many landslides occurred due to this earthquake. Okay, this is a large scale. This view of this landslide, you see near this Gopeshwar. This is the Gopeshwar town. Okay, as you go a little beyond Gopeshwar town, you can see this is the scar. This scar took place due to this earthquake-induced landslide. And what kind of landslide? This is the ground photo. That is your rock fall. Continuously, rock was falling. It is the live demonstration for days. The rock chunks are falling down continuously. Okay, and this is what is the strategy? How we study this earthquake, this hazard? What kind of your preparedness is required? First, we need to prepare a geological hazard map using the causative factors. Okay, this is a geological hazard. Then, depending on your intensity or earthquake magnitude, we can prepare the isoseismal map, and we can integrate it with the geological hazard map, and we can prepare the seismotectonic hazard formation map. Then we can understand what are the areas where the more damage is going to take place. Okay, so this is how it has been done. Okay, this is the your flow diagram, satellite image, ground information, ancillary data, topographic maps, then all the polygon maps, all the line maps, integrate, geological hazard is prepared, then MMI intensity map, integrated with that, PGI map. Okay, so in this case, liquefaction map we have not used, but sometimes liquefaction hazard potential is also need to be integrated, then seismotectonic hazard map will be prepared. Now see, in case of Bhuj earthquake that happened in 2001, the 7.7 magnitude or 7.6 magnitude earthquake, a lot of damage took place because of this Bhuj earthquake. And the same strategy we adopted. We prepared the geological hazard and seismotectonic hazard map to understand. Okay, and to understand the earthquake, also we have studied this. What is the cause of this earthquake? What is the reason of this earthquake? What are the damage occurred? Like this. This is how we need to study earthquake hazards. Now coming to the another kind of geological hazard, that is volcanic hazards of volcano and lahar. Okay, you know there are different types of volcanoes in relation to the nature of eruption, in relation to the intensity of eruption. Okay, so different types of eruption, like Pisar type is very calm, quiescent type of eruption. Then Hawaiian type, this is very little. This your force is involved. That is Hawaiian type of eruption. As you go down, Strombolian, Vulcanian, Vesuvian, then Pelian and Plinian. So intensity is increasing and it is devastating. It is very calm and quiet type of volcanic eruption, and it is devastating type of volcanic eruption. Now you see this how plate tectonics is important for volcanism. There are different kinds of volcanism can take place. One is along the convergent plate boundary. Here the island arc type of volcanism. Okay, one lithospheric plate is going down the another plate. Okay, there is frictional force is operating. There is the thermal. This effect is happening. Okay, the rocks gets melted here, and then finally volcanic eruption takes place all along the fractures. This is island arc type of volcanism. Okay, then divergent plate boundary either in the this mid-Atlantic ridge, that mid-oceanic ridge, okay, or continental extension like East African rift. Okay, so the continents are rifting apart. Here your crust is generating because of your mid-oceanic ridge where the melt is coming out. So here in this case the volcanic eruption takes place. Those are very divergent type of. Here this intensity is much less, whereas there are other kind of volcanism as well as that is known as the hotspots, intraplate volcanism. Okay, now remote sensing of volcano, okay, it is how remote sensing can help to study volcanism or volcanic hazards. That is very important for us to discuss in this lecture. You will see loss of lives are many. Okay, there are many examples of volcanoes where the loss of lives are many, and there are the worst hazards in many cases we have seen, like in case of Mount St. Helens, 1980, and there are the examples you can see. These are some of your burning examples of your loss of life and property due to the volcanism. Now, it is very important for us to understand that basic knowledge of these volcanoes. Essentially, there are around 700 or more potentially active volcanoes exist on the Earth. So, this basic knowledge about these volcanoes are not available for all the volcanoes. We have information only for few volcanoes. And volcanic hazard maps, maybe 50, 100 or so we have, not more than that. So in many cases, we do not have information, and remote sensing can help you to get this information easily. Why? There are two reasons. One is remote sensing, you can do it from a distance, okay, with selective ground truthing. And what is most important in case of volcano, unlike other kind of hazards, so you don't need to roam around, you don't need to study the entire globe, but you know these volcanoes have the fixed positions. They have the fixed geographic locations. So we can study continuously a particular area, a particular location. Okay. So that is why it is quite easy to monitor these volcanic hazards. Why? Because the location of the volcanic hazard is known to us in general. Okay. But in case of earthquake, we do not know where the earthquake is going to take place. Isn't it? And also when this earthquake is going to take place, that is also a very challenging science. In case of volcano, we can also study that, although it is also quite challenging in case of volcano also. So then when the volcano is going to happen, okay, we need to do a lot of science on that, lot of modeling on that, then only we can approach toward the reality. Now, these active volcanoes can be mapped very nicely by the remote sensing, these techniques. Why? Because active volcanoes are the spectacular remote sensing targets. Why? Because of these following reasons. Why? In case of volcano, these are the thermally hot targets. So these are thermally hot areas that can be easily identified, easily mapped on the remote sensing thermal sensors. Okay. And these clouds and plumes, in case of volcanic ash or volcanic gases, it is not similar to the meteorological clouds. It is quite different from that. Very easily you can identify that and map that. Okay. And then in case of volcanic eruption, in case of volcanoes, there are phase or unvegetated rock surface we can see. If there is a volcanic eruption, that the vegetation cannot grow immediately, isn't it? So this unvegetated area can be easily mapped, isn't it? Not only that, because of the volcanic eruption, the rock surface is exposed, and their mineralogical, textural, and compositional differences help us to characterize this type of volcano, nature of volcano. Okay, so as long as it is not covered by vegetation, and to get it covered by vegetation, it needs a lot of time. Okay, There is one more thing is important for volcanic this your sensing by this your remote sensing techniques. That is this topographic survey. If we can have spaceborne topographic surveys, repeated or multi-temporal topographic surveys we can do by spaceborne techniques, then we can understand, we can identify the topographic changes due to volcanism. Here are some of the examples you can see. So an active volcano in an optical image. It is this Landsat ETA plus pulse color composite. You can see even the smoke. And where it is more important, if we look for the shorter wavelength, the smoke will be more clear. That means band 1, band 2, these are more important. Ultraviolet, blue bands, where the smoke will be more clear. But if you go to the near infrared or short wave infrared, the smoke will not be visible. Okay, so you have to know that what kind of your satellite, these images, what kind of spectral bands should be used for a particular application. Now, you see if there is active volcano, okay, then we should definitely use the thermal sensors. You see it is the ASTAR, this visible band image, very clearly the volcanic cone, volcanic crater can be mapped using the visible bands. Whereas in the thermal band, we can see where the temperature, particularly you can see these are the volcanic bands, high temperature targets, isn't it? Volcanic bands can be identified. See here these lava flow layers that happened due to this volcanic eruption during the last 200 years in case of Mauna Loa. Okay, this is an image developed by airborne teams. Similar to ASTAR thermal bands, okay, airborne teams, there are 6 bands, whereas in case of ASTAR, there are 5 bands. Ozone band is not there in case of ASTAR, which is also there in case of airborne, because there is no ozone layer when if you fly by an aircraft, so the ozone layer is not a problem, so you can use that band also, 9.7 thermal band also you can use. So here these teams FCC, you can see these lava flows of different periods can be mapped, their age can be tentatively determined, okay, and their glassiness or composition of these lava flows can be identified, okay, from this temperature sensing only. Now, how these microwave or radar sensors are useful? Sometimes what happens, this due to the smoke, due to the dust, volcanic dust, sometimes the volcanic area is not clear, not visible, because of the smoke and dust. Okay, so it is covered by the smoke and dust. We are not able to see the volcanic eruption, volcanic cone, and the morphology of the volcano. So in such cases, the radar images are very, very useful. See here, the same this volcano in Russia. You see here it is covered by smoke and dust, whereas it is very clearly spectacular view of the volcano from the radar image. Now, by advanced radar techniques like differential interferometric SAR technique, as I already discussed with you, that is Galapagos volcano. Okay, here you see the number of volcanic cones. In some cases, you see your phase cycles. That means the deformations. In some cases, the number of phase cycles are less. Here, like here, the half of the phase cycle. Here, the number of phase cycles are there. Here, only one. Here, many. So, depending on the number of phase cycles, means deformation is more. And here the deformation means upwarding, because melt is pushing up. Melt is pushing up. Why? Through the cracks, it is pushing up, and the eruption will take place anytime. And where eruption will take place first? Where the upwarding movement is more. So depending on the upwarding movement, we can understand that here perhaps your volcanic this eruption will take place this very nearby time, whereas it may take some time in such case. Here it may take little more time. Here it may be at this moment there is no chance of volcanism. So from the upwarding movement, you can model it. And by this modeling, you can say that when the volcanic eruption is likely to take place. Okay? So this kind of science can be done if you monitor by this technique. Now, lahar, that is the volcanic mud flow. Lahar is an Indonesian term that describes a hot or cold mixture of water and rock fragments that is flowing down the slope of a volcano and on a valley. Okay, it also known as a volcanic mud flows or debris flows. Essentially it is a type of mud flow or debris flow composed of a slurry of pyroclastic material, rock debris, and water. And it can be caused due to different reasons, like it is pyroclastic flows, surges, hot basalts, okay, hot rock avalanches. It can also take place in a ice-covered area due to the melting. Volcanic eruption in a ice-covered, snow-covered area, if there is volcanic eruption, then what will happen? Due to basal melting, this your mud flow can take place. Sometimes, in case of there is a lake, and in a lake, if there is a volcanic eruption take place, then there may be mud flow can take place. Okay. Then superficial lava flows, and some cases the causes are not known. This one spectacular example is in case of Philippines, this Pinatubo, this Mount Pinatubo volcano in Philippines. No, there is this spectacular view of the lahar. This is before this volcano. Before the volcano, you see the terrain, satellite image, and after the volcano, all along the river, the lahar or the volcanic mud flow is flowing all along the river. Okay, so damaging a lot, and lot of lives were lost. This was the second largest volcanic eruption in the last century, and it is the largest eruption that affected a densely populated area. Okay, that is in Philippines. Okay. Now I am coming to this your single or lone example of the volcano in India. That is the Barren Island volcano. Okay, that is the 3D perspective view of the Barren Island volcano. There are a lot of scientific studies are going on. I am not going to much research on that because I wanted to give you what are the classical examples of volcanic studies and what are the different approaches of studies of volcanoes. And this, you see, this Barren Island volcano is a kind of this convergent plate boundary island type volcano. Oceanic crust is going down under the continental crust, and this island type of volcanic eruption is taking place in this case. Now coming to the anthropogenic geological hazards like coal fire, okay, like mining subsidence, like groundwater depletion induced subsidence or aquifer compaction induced subsidence. In this case, you see the geological hazards due to anthropogenic regions like coal fire. Coal fire, you know, in case of India, the Gandona coal pits, there are 54 coal fields in the country. You see, these are the coal fields are shown, individual coal fields. And many of these coal fields are fire affected. And the worst affected coal field is the Jharia coal field, followed by Raniganj coal field, Talcher coal field. These are all fire affected. Okay, so we have studied and we have identified using multi-temporal this thermal image. Okay, that what are the wherever is the coal fire is observed. Okay, and how the coal fire is changing, spatiotemporal dynamics of the coal fire. Now you see for the Jharia coal field, see we have studied the coal fire scenario during the 1990s at different times, and this is post-2000 period at different times, how the coal fire, this area is changing. You see initially it was reducing during the 90s, but again there was increase in post-2000 period. Now again there is some increase, again there is decrease and increase, so it is very much fluctuating. There are a number of factors involved in this. Intensity of mining, how this your elevation measures are operating, how this your other factors like your mining I have already discussed. So how you are removing these fire affected these coal seams, all those things are very, very important. So here you see this surface coal fire, subsurface coal fire. And the surface coal fire particularly you can very precisely identify. There are techniques available. Okay, that is the shortwave infrared bands you can use and you can identify the surface coal fire locations. Here you see I have shown you this part of the Jharia coal field. This is the location of the Jharia. Okay, and this red is the surface coal fire locations, and this is yellow is the subsurface coal fire. And here this is the thermally anomalous zones, but these are transitional. There is no coal fire at this moment, but it is vulnerable to coal fire. Anytime there can be coal fire in such areas. Okay, this is the map prepared based on 2005 data, and this is the map prepared based on 2013 data. Now you see some of the field photographs, analog photographs taken long back, but you can see it is still, it is very, very spectacular views of the seam fire, this is the debris fire, this is a subsurface fire, smoke is coming out, and there are wide open cracks. You can see this is subsurface fire. Due to that, there are subsidence of the land surface is taking place. Okay, so this kind of things you can understand. Now, mining subsidence. Why mining subsidence takes place? Because of underground mining, because of underground coal fire, isn't it? Because of abandoned mines, that is the galleries exist, that gets waterlogged. Okay, there are the pillars, coal pillars exist, that is weathered because of the waterlogging. There are many other cases because of depillaring, because of caving, that is the secondary mining, the subsidence can take place, isn't it? Now, you see, this is the advanced differential interferometric SAR technique, C-band and L-band data we have used and identified in case of Jharia coalfield. What are the subsiding areas? What is the purpose of this study? Purpose is, here the slow movements, if we can detect before this roof collapse takes place, we can identify the vulnerability. This is the area where the roof collapse can take place and we can save life and property. So this is the purpose. Okay. Here, you can identify the slow movement, slow land surface movement in C-band, whereas the L-band is capable of detecting these high-speed movements. Okay. So this is the purpose why we have used both multi-frequency, multi-wavelength differential interferometric SAR techniques. And based on that, you can prepare this your subsidence map from the differential interferometric SAR technique, and this is the rates of the subsidence, and this is prepared based on the ground-based survey. And this is not by us, this is prepared by the coal mining agency, Bharat Coking Coal, by the different coal mines, by the different area offices, different colliery offices. They have prepared this surface plan, and we have just digitized, we have georeferenced, we have mosaic together and prepared this your integrated, okay, this subsidence or this degraded map. Then we have compared. Now I'm coming to this anthropogenically induced this hazard, that is the urban subsidence due to groundwater depletion. You know, there are more than 150 cities in the world are reported to have serious problems of land subsidence. Why? Due to excessive groundwater pumping. And that data is 2004 data. That is more than 16 years back data. Okay? And many more cities are affected by land subsidence before and even after this report. Okay? Some are reported also recently because there are many studies are happening. And many are not still reported because of lack of scientific investigation. There are the reported these areas where the land subsidence are taking place because of the exorbitant, I should say, exorbitant groundwater depletion due to the pumping. Pumping for to cater to the city population, pumping particularly for the agricultural irrigation. Okay, in many areas, you know, northwestern part of India is highly depleted in terms of groundwater. Why? To support irrigation to the agriculture. Okay, and many cities also, there are a lot of pumping taking place. Sometimes industries also they use groundwater a lot. Okay, but most of the groundwater depletion is caused due to the pumping or irrigation to agriculture. These practices. This is one example. You can see here. This is one example, geological urban subsidence. I'll come back to your questions. Okay, just I'm going to finish now. Some of you, maybe you are sending some questions, isn't it? I'm coming to your questions very shortly, in a few minutes. So this is urban subsidence. This is one example of Indonesia, Bandung city. You see here, in Bandung city, we have studied using this, again, this radar technique, GPS technique, as well as hydrogeological technique. Aquifer compaction, we have mapped. If this groundwater pumping is taking place, how much groundwater is depleted, what is the geological materials, how much is the aquifer compaction will take place, how much is the your confining layer compaction will take place, elastic compaction, inelastic compaction, all those things we have estimated based on the model. Then from differential interferometric SAR data we have used and identified these land subsidence at the surface, and GPS technique we have used to measure continuously over this area, this land subsidence. Our counterpart from the Bandung Institute of Technology, they did this GPS survey. We did this DINSAR and this your hydrogeological this modeling, that is aquifer compaction. And you see, this is the results. You see here, almost 15 to 20 centimeter this per year, the subsidence taking place. And the results are very much agreeable in case of differential aeromatics, GPS, and this isometric compression, that means aquifer compaction due to groundwater pumping. The another example is in case of Iran, that is in Rafsanjan city. In Iran also there are exorbitant groundwater pumping taking place for the city population and mostly for the cashew cultivation. Okay, the rainfall is very, very less, 100 to 200 millimeter rainfall, and groundwater pumping is exorbitant. You see this groundwater level decline in some of the wells during 2002 to 2008 data. Okay, this is one of our students studied. Similarly, Bandung also studied by one of the student, Indonesian student. This is studied by one of the Iranian student. And here you see we have identified this area where this subsidence zone we have identified. Similarly, we have done this study for different Indian cities like Kolkata, like your Delhi, like your Chandigarh, many other cities we are working on. Okay, so here you see what is the kind of damage it did due to this aquifer compaction and land subsidence. You see, this is the well, your casing. Here see the size of the cracks. Similarly, in case of Bandung also, you can see the cracks on the road, and this is the well casing. What is happening to that? Okay, so these are your extent of damage because of the your geological hazard. Essentially, this is a geological hazard due to anthropogenically caused geological hazard. So this is all. I would stop now, and I'll take your questions now.